To begin, Newton's method is the approximation of a solution of a differentiable equation within a given interval. Its formula is a rewritten form of a tangent line in order to find the best estimated solution. This method is used in real-world situations involving civil, electronic, and many other types of engineering. Let's begin by obtaining our formula using the tangent line equation.
Now, to obtain a better grasp on how Newton's method works, we have a square root function on a graph in quadrant 1, and we're going to use an initial guess that it's going to be an x value near the real solution in order to approximate the real solution. Now, from that initial guess, we're going to draw a line that's perpendicular to the function in which we can find a value and create a tangent line. From that tangent line, we're going to follow it all the way through the x-axis to find another solution that's even closer to the real zero in order to approximate another. And from that iteration, we can go ahead and repeat the process infinitely just by drawing a line up to the function and continuously making tangent lines crossing through the x-axis. Let's start by looking at our tangent line in order to find our Newton method's formula. So that way we can recreate our iterations to however many needed. Here we have y equals f prime of x times x minus x1 plus f of x. We're going to plug in 0 for y so that way we can isolate x. The first step would be to subtract f of x from both sides of the equation. After doing that, you should end up with negative f of x equals f prime of x times x minus x1. To follow, we're going to divide both sides by f prime of x in order to isolate the set of parentheses. Once that is done, we should get to a step where we can then move over x1 to finally get a set equation that is x1 minus f of x divided by f prime of x equals x. And then there we have it, our equation for Newton's method. From there, we can begin to solve any other problems in however many iterations asked for by using an initial guess. For our first example, we're going to be using Newton's method to determine x2 with the given function f of x equals x cubed minus 7x squared plus 8x minus 3, and the initial x value, which is going to be 5. We're first going to find our f prime, which is going to be 3x squared minus 14x plus 8 from the given function, so that way we have the equation on hand for when we're trying to plug in our values into Newton's method's formula. Next, it would be wise to write down Newton's method's formula so you know which values to look for before you plug them in. And it's going to be xn plus 1 equals xn minus f of xn over f prime of xn. Next, we're going to plug in our x initial so that we get x1 equals 5 minus f of 5 over f prime of 5. Then find f of 5 and f prime of 5 separately by using the equations we have up above. After plugging in f of 5, we should get 125 minus 175 plus 40 minus 3 equaling out to negative 13. Then, while finding f prime of 5, we should get 75 minus 70 plus 8, all equaling out to positive 13. Once we've found those two values, we can then plug them back into the original Newton's method formula that we had from the beginning, making it easier to get our iteration. So then, we should have 5 minus negative 13 over positive 13, which gives us 1. Then adding that to 5, we should get the value 6, thus giving us our iteration. Now, after finding x1, we can continue on Newton's formula by finding the second iteration and plugging it in. That should give us x2 equals x1 minus f of x1 over f prime of x1. Since we know that x1 equals 6, we can then plug in that value and find the rest by plugging them into our other equations, giving us x squared equals 6 minus f of 6 over f prime of 6. Next, we're going to find f of 6 and f prime of 6 by plugging them into the prime and the original equation. By doing so, we should get f of 6 equaling out to 216 minus 252 plus 48 minus 3, giving us a value of 9. And to find f prime of 6, we would also plug that into the other equation, giving us 3 times 6 squared minus 14 times 6 plus 8, equaling out to 108 minus 84 plus 8, giving us a value of 32. Once we have those two values there, we can then plug them back into the equation that we were working on before, giving us x2 equaling 6 minus 9 over 32, giving us our x2 using Newton's method, which is the iteration that we were hoping to get. In our second example, we're going to be using Newton's method to find x of 2 with given values. We're given our x initial, f of 8, f prime of 8, f of 10, and f prime of 10. We're going to write down Newton's method's formula first, so that way we know which values to be looking for. We're going to have x of n plus 1 equals x of n minus f of x over x prime of x. Our first initial iteration is going to be x of 1 equals x of 0 minus f of x 0 over f prime of x 0. Since we have all these values, we can go ahead and plug them in by first substituting our initial x. That's going to be x1 equals 10 minus f of 10 over f prime of 10. And once again, since we have these values, we can go ahead and plug those in as well, giving us 10 minus 4 over 2, giving us a value of 8. Next, to find our second iteration, we're just going to repeat the process. Now that we know that our x1 equals 8, we're going to find our x2 by plugging that into Newton's method formula. Now with the second iteration, it's still always good to write down Newton's method's formula, which should give us x of 2 equals x of 1 minus f of x1 over f prime of x1. Now, after that, we can go ahead and substitute our x1 in since we have found the first iteration, giving us x of 2 equaling 8 minus f of 8 over f prime of 8. And since we're given f of 8 and f prime of 8, we can plug in those values as well to give us 8 minus 16 over 4 equaling 4. And that concludes our second iteration for this example. For another example, we have a more realistic situation in which we're calculating the height to which an 8-foot-long dipstick would be wet with oil when immersed in a spherical storage tank containing 6 cubic feet of oil. Before we begin our first iteration, we're going to write down two formulas. We're going to write down the formula that they gave us for height, which is f of h equals h cubed minus 9h squared plus 3.8197. After that, we're going to find the f prime. And then the f prime is going to be f prime of h equals 3h squared minus 18h. Now using these two equations, we'll be able to plug in all our values that we need for Newton's method. Now we need to begin with an initial guess. They didn't give us an initial guess, so the best possible guess that you could take would be something that's close and also a whole number to the value that you're looking for. Now the initial guess here would be h0 equals 1. Now using that guess, we're going to start off and estimate the root using Newton's formula. We're going to write down the equation first, and that's going to be h1 equals h0 minus f of h0 over f prime of h0. Now, in order to get these values, we'd have to plug them back into the equation to make sure that we can get what we need to in order to solve it. Well, I'm going to go ahead and plug them in to the equation while keeping it in Newton's method's formula at the same time. So that's going to give me 1 minus 1 cubed minus 9 times 1 squared plus 3.8197 all over 3 times 1 squared minus 18 times 1. Now once you solve this out, you should get 1 minus negative 4.1803 all over negative 15. And once you solve out that last step there, you should get 0.72131, which is going to equal your h1, which completes your first iteration. To begin our second iteration, we already have our equations that we need. We have our height equation and our prime. We also have our initial value as well as our first iteration value. From there, we can go ahead and write in what Newton's method's formula is going to look like for our second iteration. It's going to be h2 equals h1 minus f of h1 over f prime of h1. From there, we can go ahead and plug in our values into the equations and plug those into the formula. And that's going to equal 0.72131 minus 0.72131 cubed minus 9 times 0.72131 squared plus 3.8197 all over 3 times 0.72131 squared minus 18 times 0.72131. It sure is a mouthful, but that's the step that we're going to have to complete before we can reach our h2. So after solving out the fraction, we should get 0.72131 minus negative 0.48764 all over negative 11.423. Now to simplify it as much as we can, just so that we can have a more accurate h2 value, That should take us to 0.72131 minus 0.042690 to give us our final answer of 0.67862. Now, to complete our last iteration, we already have our equations written down like so, and we also have our other iteration values as well as the initial. And our equation for the Newton's method for our third iteration is going to be H3 equals H2 minus f of H2 over f prime of H2. And from there, we can go ahead and plug in all our values. That's going to be H3 equals 0.67862 minus 0.67862 cubed minus 9 times 0.67862 squared plus 3.8197 all over 3 times 0.67867 squared minus 18 times 0.67862. From there, we can only simplify and go ahead and plug in all our values until we get a more accurate answer, which is going to be 0.67862 minus 0.0011572 to give us our final third iteration of 0.67747. And that concludes that iteration for that example. And that also concludes our video for how to approximate a solution by using Newton's method or iteration.